There's a mystery at the very heart of the universe. We don't know how old the cosmos is.
Understanding the age of the universe is fundamental to understanding the universe at all.
It's at the heart of everything.
It's more than just celebrating a birthday.
We want to know how much mass is in it, how much energy is in it, how it behaves. We have to have this number nailed down.
The age of the universe enables us to not only understand where we came from, but potentially the fate of the universe, what will happen millions and billions of years from now.
But our quest to discover the age of the universe is starting a war.
Usually nature just whispers to us. Now nature is screaming in our ear that we're doing something wrong, and that's exciting.
We think the universe started with a bang.
Everything that has ever existed is squashed up in the space smaller than a pinhead. And all of a sudden, space just starts expanding everywhere at once.
The idea that the universe grew from a ball smaller than a pinhead is hard to understand. But figuring out when it happened sounds like it should be more straightforward.
It seems like a simple question, right? But it turns out getting the age of the universe is pretty tricky.
Scientists have just a single fact as their starting point. The universe is expanding.
When people realized the universe was expanding, they thought they finally had a way to estimate the age of the universe. Take the universe now and run it backwards in time. Things get closer and closer till they come to a single point. That time to that point is the age of the universe.
The expansion rate is so important, it's been given its own name, the Hubble constant.
The Hubble constant is the present-day expansion rate of the universe. It is a key ingredient to understanding the entire expansion history of our universe and its age.
Scientists discovered a strange radio signal permeating the cosmos. It's the remnants of ancient light from the early universe. We call it the cosmic microwave background, or CMB for short.
The cosmic microwave background radiation is simply the afterglow of our Big Bang, the way the universe looked when it was 400,000 years old.
The European Space Agency launched the Planck satellite. Using sensitive radio receivers, the orbiter studied the sky in every direction, measuring tiny changes in the temperature and polarization of the radiation signal.
The CMB has all these variations in temperature, and they're not randomly generated. They are there because of physical processes that occurred when the universe was in its primordial fireball phase.
The red blobs are where matter was hottest, and the blue areas are where matter was cooler. The smallest red blobs are where hot material was packed tightly together.
That's where material in the universe would have been denser, and that's where galaxies would preferentially form.
It's so cool to get to look at those blueprints and study them and see how that baby universe later grew up into the universe we see around us today.
Although it doesn't look like much, hidden within this picture is almost everything we can know about the universe. In a complex process, using different mathematical models, cosmologists figured out how the ancient cosmos captured in the CMB became the universe we see today. They worked out how the universe got from small to big, and how fast that expansion happened.
The data from the cosmic microwave background is absolutely the gold standard for cosmology. It's beautifully clean, we can understand it really well, and we have a lot of confidence that what we learn from it is pretty robust.
By running the expansion backwards, we get an age: 13.82 billion years. Job finished. But it's not quite a slam dunk. The figure must be verified.
We don't make a single measurement using a single technique. We make multiple measurements via multiple techniques.
Another group of scientists use a totally different method to calculate the age of the cosmos. measuring objects that we can see in our universe to determine how far away they are and how fast they're moving away from us as the universe expands.
The most direct and most accurate measurements are using what is known as parallax. Parallax is the apparent shift in an object relative to the background when it's viewed from two different locations.
So if I look at my thumb with one eye, and then I close it and look at the other eye, it looks like my thumb moves.
If I move my thumb closer to my face, then the distance it moves back and forth changes. It appears to move back and forth more.
That parallax difference as we move the thumb closer and farther from the face is the way we measure distances to distant objects.
Using parallax, we can measure the distance to bright stars called Cepheids in the Milky Way.
Cepheids are stars that burn 100,000 times brighter than our sun. So they're extremely bright and they pulsate, meaning they get brighter and dimmer over a regular time period.
Cepheids that pulsate at the same rate have the same brightness. They're known as a standard candle.
A standard candle is something that is a standard, meaning we know how intrinsically bright it is. So all we have to do is measure the brightness that we appear to perceive on Earth, and then you solve for the distance.
So imagine that you're on this street. By looking down the street, you'll see that the street lights get dimmer and dimmer the farther away they are. But that's not their intrinsic brightness. Their intrinsic brightness is the same. So by seeing how faint the farthest away ones are, you can understand how far away they are from you.
We can use standard candles to measure the distance to stars farther away. But there's a big problem. Throughout the universe, there's a competition between the expansion, pushing things apart, and gravity, pulling things together. In the Milky Way, there's so much matter that gravity wins. Even looking at galaxies in our neighborhood, the expansion is tiny. But at cosmic scales of very different galaxies, matter is more spread out and expansion wins. So we can only measure expansion over massive distances.
The way we start to measure distances to things that are farther and farther away is to use something we call the distance ladder.
Each category of object that we observe is on a separate rung of this ladder. Measuring the distance to one will then inform us how far away the second rung is, and then the third rung. So each rung depends on the previous rung. And from stacking these together, we can start to measure things very, very far away from us.
Using parallax to measure Cepheid stars in the Milky Way gives us a benchmark. We can then use their standard brightness to measure Cepheids in other galaxies. The next rung is a brighter standard candle called Type 1a supernovas. They can be seen in galaxies farther away. Finally, we can measure light from distant elliptical galaxies. And by looking at how red the light is, we can work out how fast they're moving away from us.
So those three things give us the nearby universe, the somewhat far away universe, and the very distant universe, rung by rung.
March 2021. Scientists measure the light from 63 giant elliptical galaxies, the farthest rung of the distance ladder. They hope to get the most accurate measurement of the Hubble constant to date and a precise age for the universe.
The light that comes out of an object can get shifted if it's moving. If an object is moving away from us, then those wavelengths will get stretched out down into the reds.
So, as the universe expands, distant galaxies look redder than expected. It's known as redshift.
Redshift is very similar to the Doppler effect. That's something a lot of us are familiar with. That's where you have a siren. If something's moving away from us, we'll hear its pitch drop. Or if we have a car that's moving towards us with a siren, the pitch will go higher.
The team used the redshift of the elliptical galaxies to work out the age of the universe. Their calculations make the universe 13.3 billion years old. not too far away from the figure of 13.82 billion years given by the cosmic microwave background, a difference of around 6%.
That sounds trivial, but that equates to hundreds of millions of years of cosmic history that either happened or didn't happen.
50 years ago, when we weren't quite as good at measuring everything about the universe, we would have been thrilled to have our numbers agreeing to this level. But nowadays, having a difference like this, it's unacceptable.
Clearly, the two techniques do not agree. Cosmologists split into two camps.
We had hoped that these two methods were like building a bridge from either side and then meeting in the middle, but they're not.
Now we know that something is going on we don't understand.
Even though these measurements are roughly the same, it's really dangerous to just accept them and assume that everything's fine. Because in science, usually the initial really big discoveries start off as small differences that then you pull on that thread and something wonderful emerges.
So, does a simple question, how old is the universe, unravel everything?